All right, we're in building 26. Great to see you again, Mark.
Good to see you, Charles.
How are you doing?
Good, thanks.
Excellent. So you've been here for 3 years now, a couple releases. How are you feeling? Hanging
good.
in there?
Really good. Yeah, hanging in there, excited, looking on forward to the next thing.
Cool. So speaking of the thing that's here now, I mean, it's GA, general availability, which of course, you know, it's kind of an important day for you guys, right? Everyone can get their hands on this great operating system that you've made in Windows 7. Last year, for PDC timeframe, we talked about what was new in the kernel, because you guys had actually done a fair amount of work, but we didn't cover it all. So I wanted to come back and chat with you about some of the stuff we didn't get to. We covered all the high, big impact stuff, but we missed some things, so I wanted to get...
We actually missed a whole lot of things. We said the next level down is just a whole ton of things.
Beautiful.
And, the things that I focus on talking about are really the system related stuff, I'm not, you know, super bar and other things like that.
Absolutely.
But there's a lot of stuff that's above the things that I talk about too, which obviously we're not going to get to today.
Sure.
But yeah, like you said, we covered a lot of the big things, like we touched on core parking, we talked about greater than 64 processor support and the dispatcher lock being gone, and I know you talked to Arun about that. Speaking of that, I got a 256-way system here, and I can talk a little bit more about how we did the greater than 64 support too, and show you that.
That would be great.
What else did we talk about last time? So, the trigger started services, and you talked
boot
about
from
that.
VHD.
Yeah, boot from VHD. I talked about timer coalescing too as a way to minimize, to maximize idle periods.
Yes.
There were some other timer things we did that I could talk about today, including one that we did for Hyper-V as well, and I can talk about what else related to Hyper-V. Live migration, which is a key feature in R2's Hyper-V. Talk a little bit about how that works behind the scenes. There's a whole bunch of things. So
good. And one of the things that we talked about, I think we've talked about it in every single interview that we've done since you've been at Microsoft, because you, along with Rich Neves, have been thinking about, you know, modularization, trying to understand the beast.
Yeah.
Is min-win, right? We talked about, I think everybody knows what it is. So we talked about it last year, and Mary Jo Foley wrote about it, and everyone was like, wow, so min-win is in Windows 7, blah, blah, blah. But it's not something that consumers care about. We don't use it.
Yep.
But I just wanted to kind of get it out there. I mean, why does min-win matter to you?
It matters to us because for a few reasons. One is engineering.
Sure.
When it comes to testing the lowest levels of the system, previously we'd all have to test entire Windows to test just the parts at the bottom. And the more software you've got up and running around your tests, the more interference they can cause and problems with the test process. So if we can boot min-win and test just the pieces in min-win independent of everything else, we can get more reliable tests.
Excellent.
And more efficient tests. And min-win's really small, so we can deploy it very quickly. So there's engineering efficiency with regard to that. And then there's kind of looking long term with what we learn from min-win and where we can go with it. Because I mentioned that things like server core, Windows Embedded, and Windows PE, these trimmed down versions of Windows are all based on what we call slice and dice, which is just taking full Windows and then pulling DLLs off it until you just believe you've got the functionality that your scenario that you're building on this thing needs. So for server core, they go and make sure that the server roles they want are only the DLLs and parts of the system they need for their server roles are actually there in server core. But the problem with that approach is that as we change the system and move DLLs, introduce new DLLs, split DLLs, that we end up breaking the previous definition of these things. So Windows PE team and the Windows Embedded team and the server core team, every release, they've got to go reset what those things look like and retest and figure out these server roles still work. So because at those layers we don't have a good idea of the dependencies between an API in a DLL over here and another DLL way over here. In fact, if you remove this DLL, then you could end up breaking something way across the system. Totally. So with min-win, we understand perfectly the dependencies between min-win and the rest of the system. In fact, there's none between out of min-win to the rest of the system. So it's completely independent, self-contained. And if we keep on going, min-win doesn't have enough functionality to actually build a product on top of. But if we keep going up the stack with what we've learned, then you could get to the point where you could have a server core type version of Windows where we do understand the surface and it is self-contained from a dependency perspective and testable by itself, so that it doesn't end up breaking as we continue to evolve the system. And it also is a smaller footprint, because server core today, because of this intertwining of all these DLLs, you end up having an image that's much larger than what's really required to provide the functionality that the server's roles want, just because there's extraneous dependency chains that go through DLLs, DLLs that have functionality in them that's really not used, but needs to be there to satisfy this dependency map.
So, I mean, I remember back in, I think it was the December of 2005, when Robert Scoble and I did an interview with the once VP of this org.
Yeah, Rob Short.
I really liked Rob Short. He's retired, he's smart, he's surfing or something. And Rich Neves was there. At that time he was an architect, not at the company for that long. And his whole thing was figure out the dependency map.
Yeah.
So apparently you guys have done that. I mean, it's 4 years later. And so what I'm hearing is you've done that. We understand. So can you confidently say we understand the dependency tree of Windows?
Depends on what you mean by understand.
Well, so let's,
yeah. So we do have the dependency map, and that was the first step to looking at the system. And it's kind of interesting because Windows evolved ad hoc over the years. You know, people just add components, and there was no attention paid to architectural layering in the system. So people would write a component and they'd say, well, there's an API over here in this DLL that does what I want, so I'm going to just call it. And from an architectural layering perspective, they might have been calling APIs in a DLL that were way higher in the layering, logical layering that should have been applied there. And so that's created this big tangle of dependencies that Windows ended up being. So the first step was using these tools and scripts that Rich and Rich Pletcher ran on Windows to understand the dependencies between binaries, and then reverse engineer what the layers look like. So what they did is, just by looking at the number of connections between DLLs, in some places looking and saying this DLL logically belongs lower in the system than another one, they derived this layer map, we call it, of Windows. And then the next step was, okay, let's make some use of this and what we've just talked about. And so they looked at cutting off the bottom of the layer map and saying that that's MinWin. And that required refactoring at the edges that they broke, where there was pieces, these DLLs straddled the line basically between what they wanted in MinWin and what shouldn't have been in MinWin, outside of MinWin.
So one question I have, and I didn't ask back 4 years ago, and I guess I haven't asked you either, is in some sense, I mean, the Windows kernel is a large kernel. My question to you would be, as the kernel seems to be getting bigger, with Windows 7 as an example, I guess what I'm trying to ask is, why couldn't we just have, how many of those dependencies and the problems that you're speaking of are in kernel mode, or what you call the kernel, which I know is not the same as what some people may think of it. But can we talk about that?
Well, so yeah, from the kernel mode perspective, we didn't take, so kernel is an overloaded term, especially in Windows. Actually, there's a generic operating system kernel which people refer to as just the core operating system subsystems that run in kernel mode. So that is NTOS kernel, this image NTOS kernel, that contains the memory manager and the plug-and-play subsystem and the power manager, the I/O system. Within that, we've got a component that's actually called the kernel, that they've named the kernel, which is the lowest layer core component inside of the kernel.
Okay.
So that's a little bit overloaded, but we didn't. The NTOS kernel image we didn't break apart. But running in kernel mode, there's a lot besides just NTOS kernel. There are a lot of drivers that are really part of the core operating system that are just not part of that kernel image.
Okay.
We didn't break any of those apart either as part of MinWin. They're all at the lowest layers of the system. What MinWin does is says that some of those drivers are optional in MinWin. You don't need them in MinWin. So you could, but from a dependency map, we didn't do any refactoring at that layer.
Okay.
So the refactoring is, of course, that we had to do for MinWin is at that line in the layer map, and that's all in user mode. So I think last time I probably talked about one of the DLLs that got split is kernel 32.
Okay.
And kernel 32 is one of the core DLLs. It's the interface for the I/O functionality of the kernel, for the memory management functionality of the kernel. And there's a bunch of those APIs that are implemented in kernel 32 that fell out of what we wanted in MinWin. So we had to cut that DLL apart and create a DLL that's in MinWin, but preserve kernel 32 as a DLL that has all the same exports up outside of MinWin, because we needed to preserve application compatibility.
Okay.
So in the version of the DLL that's in MinWin that implements the kernel 32 functionality specific to MinWin is called kernel base. We also, at the same time, took a step towards separating an API set from the DLL that actually physically implements or logically implements it.
Okay.
So one of the things you've seen as Windows has evolved over time is as part of helping the boot process, we want to minimize the number of DLLs. The more DLLs you have, the longer it takes to load each one. So what you've seen is, if you look at a DLL like kernel 32, and there's some others that are more extreme examples of this, lots of API sets that are unrelated to each other that are in the same DLL.
Okay.
And that's done for performance, not for architectural reasons.
Okay.
So we came up with this concept called API sets, where we say, okay, there's an API set, and the system now has this notion of virtual DLLs that implement an API set. And the loader knows about this. So within MinWin now, components link against an API set, a virtual DLL, not an actual logical DLL.
Huh.
And when they reference this virtual DLL, the loader looks in this mapping file called API set schema.dll, which is sitting in the system32 directory that it loads in during boot, and says, oh, this virtual DLL is actually implemented inside of this logical DLL. So it might call an API set, an API in the file system, the I/O category.
Okay.
And the virtual DLL is API set dash something, then we've got this naming scheme, dash kernel sat dash file system, or I/O, I can't remember what we call it. And so the loader says, oh, that virtual DLL, API blah 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 dot DLL, is actually implemented in kernel base dot DLL. And so it'll link up the images together that way. And so that's another thing that we've done there. The foundational work, again, not really interesting from an end user perspective, but it's actually visible in the system because you can see API set schema, you can see kernel base.dll in the system, and the other refactored DLLs are there as additional DLLs in the system.
That's awesome, though.
And actually, kind of interesting, the refactoring of the DLLs to create MinWin, it did improve boot time, because you ended up with components loading a DLL that was larger than it needed to be, because it had a bunch of these API sets in it in previous versions of Windows, and now they load a smaller DLL. And in some cases they load fewer DLLs because this larger DLL that has a bunch of API sets in it an API set might have had a dependency on another DLL that also would get loaded at the same time. But since you're not loading that API set, you're loading another one, then you're avoiding that second DLL.
Excellent.
As well. So there was performance benefits to MinWin.
Perfect. And now, of course, listen, one of the things I've really noticed in Windows 7, and this is not marketing crap, is the fact that A, it boots faster than any other version of Windows that I can remember, and B, it actually shuts down when you ask it to shut down. You don't sit there and look at a donut. And secondly, the resume speed blows my mind from hibernation compared to Vista. And that's because, obviously, like you're saying, you're loading less junk based on what you were doing at the time. But still, I think that's amazing. And partly what you just said is something I don't think anyone really has realized. A little bit of it is due to API sets. A small amount, like you just said.
It's a whole ton of things that went into it, right?
Of course.
We parallelized the boot further than we did in Vista.
I heard about that. Is that true? Somebody told me that the image was actually a serial. So you guys were blocking while that image was loading. Nothing else was happening. Is that true?
There were places in the Vista boot process that were parallelized. There was more work done, and there was also a lot of work done on boot prefetching. that had started in Vista that was further improved in Win 7 as well.
Okay. So let me ask another question in terms of parallelizing. In Windows 7, did you spend much time figuring out what could be parallelized that was currently not being parallelized in Vista? I mean, do you ran tools and got an understanding of all of this? Most people are running quad cores on their desktops now.
Yeah, no, there was definitely work in parallelizing in the places where it's obvious to parallelize, up in codecs and things like that.
Okay.
A lot of the work at the core kernel level, the kernel's always been highly threaded, so a lot of the work there was just getting rid of the bottlenecks. And we talked about some of the locks that were removed, like the page frame database lock that Landy removed.
Now, we didn't talk about that.
We didn't talk about that one.
So let's talk about that one.
There was a number of locks that were removed. The big one we talked about was the dispatcher lock.
Yes.
That Arun got rid of, and you had a big interview with Arun about the details on that.
Totally.
So, but there was a number of other locks that were removed as well. So,
let's talk.
Arun removed the dispatcher lock, and Landy said, "Oh, Arun removed the dispatcher lock. I've got to go remove my lock too." So he went and removed the page frame database lock. And
wow.
That lock protected the state transitions of physical memory. So there's this database in the kernel that it uses to keep track of the state of each page of physical memory. And by state, I mean, is it part of the process's working set? Is it on the standby list? Is it on the modified page list? Is it free? If an application frees its memory, it goes to the free list. So whenever a change was made to any state, then the page frame database lock was grabbed. The change was made and then it was released. So if you had a system where there was lots of changes going on in parallel, like on a big multiprocessor that is doing a lot of address space stuff, then you would end up contending on that page frame database lock. It wasn't as big as the dispatcher lock, of course, but once the dispatcher lock's gone, these other locks start to show up as locks that get hot. So he removed that lock, and now each page is protected by its own lock.
Nice. Which, I mean, and what other, we didn't really talk specifically about other things Landy has done. I mean, in your book, the Windows Vista, inside the Windows Vista kernel, which we had on channel, we talked about briefly on Channel 9, as a co-author. There's a section on there about memory management. What in Windows 7, besides the page frame lock removal, what has Landy been up to, man?
He's actually done a bunch of cool things.
Okay.
And some of the things he's done actually do have very visible benefit. One of the things he did is, if you look prior to Windows 7, there was something we called the system working set, which actually consisted of 3 separate kinds of memory that were associated with stuff in kernel mode: pageable pool, pageable drivers, and physical memory that was being used by the cache manager's virtual mappings, so the virtual cache manager. And the fact that all of these 3 things were lumped together in one working set meant that there was special case code in the memory manager that treated it special, tried to protect it, because it's something that's pretty critical to the performance of the system in general, and you don't want some app blowing it out and then all that stuff going to the paging file and having to be brought back in. You want to try to favor that stuff. But the other problem that it caused is if you had a large file copy where the cache manager ended up allocating large parts, blowing through a lot of physical memory, it would end up pushing out all the pageable code and page pool out to the paging file. And then your system ends up thrashing as that stuff comes back in after the file copy. So what he did in Windows 7 was to break that into 3 separate working sets. And a working set, by the way, just to clarify what I've been talking about, is the physical memory that's assigned to a process, or some particular memory usage, like the ones that I've been talking about. So the memory manager's job is to share physical memory across everybody that needs it, different processes and these system regions. And so Landy's got finely tuned algorithms for, if a process looks like it's paging a lot and other ones aren't as much, then let that working set grow, shrink other ones. So, like I said, he had a special case for the system working set previously, and now that it's been broken up into real working sets that are just like any other process working set, there's no more special case code for it. They're just treated just like every other process working set.
Excellent.
So that was probably the big thing he did, but he also improved the efficiency of the page aging algorithms. So when memory starts to get low, physical memory starts to get low, page aging turns on in the operating system. And page aging is used to guide the memory manager when it needs to trim a process because somebody else needs memory. It wants to trim the least recently used pages. Okay. And to know what's least recently used, it needs to age accesses. So what it does is goes through physical memory and clears the access bit. And this is something called the clock algorithm, which Unix memory managers do too. Then if application touches its page, the access bit gets triggered by hardware. Memory manager comes back through on another sweep and sees that the access bit's been set, and then says, okay, this guy should move to the most recently used line. And if it hasn't been set, well, then we age him a little bit. We say he's older because he hasn't been accessed. And so he improved the efficiency of those algorithms, and he also found another extra bit to use for aging. So there was four levels of aging. So a page could be, 0, 1, 2, 3 age old, right?
Okay.
So he added an extra bit, so now there's 8 levels of aging. And the more levels you get, the better decisions you make about what's least recently accessed and not. So again, in the case where memory gets low and things are getting thrown out, the system's a lot more intelligent about what it should be throwing out versus what it should be keeping.
And this is memory that's living in RAM.
Yeah, this is RAM, physical memory.
Of course.
Yeah.
Which is a big deal.
Yeah.
So I never really think about this. I mean, we talk a lot about scalability to many cores.
Yeah.
But how does the memory manager? Is there a similar concept to the memory manager scaling to, like, if I have a terabyte of RAM?
Yeah.
Is it going to just do different things? Because I have all of this at its disposal. Maybe it can, I don't know, increase how long something can live. I mean, is there sort of a dynamic?
There's not too many places in the system where it changes its behavior based on how much memory there is. There's calculations that it does based on the amount of memory, where it will, low memory means something slightly different on a terabyte machine than it does on a system that has a gig of memory.
Sure.
So then that's just based off calculation.
Okay.
It's kind of interesting, actually, if you go look at the source code, there's, back in the early days of Windows, back when we had really small machines, there was definitions that Lou Perezzoli, the original memory manager architect, had put in where he did change behavior based on how much RAM was in the machine. So a small system was 12 megabytes. A large system was more than, I think it was 64. And so those code paths are still in, some of those code paths are still in there.
That's amazing. So that actually brings up a great point, because we talk a lot about Windows.
Oh, actually, speaking of the terabyte system, I've got this.
Let's do that.
Yeah, if you want to see one in action.
But while you're loading that up, I guess what I was asking was, how much longer are we going to have code from the early days in Windows? I mean, granted, some of it's probably pretty amazing, like Cutler's stuff. You not necessarily want to rush to take that out. I mean, he's one of the world's best software developers.
When it comes to code that's old, you've got to be very careful.
Sure.
You've got to be very careful removing code from the system, just in general, because application compatibility is a huge thing. You remove code, you've got to know for sure that nobody's dependent on the behavior that code is causing or the functionality that code provides.
Fair enough.
As far as the 12 meg, 64 meg checks, I don't, maybe Landy's busy adding, cool features and hasn't bothered, because it's really not causing any problems. It's not causing any footprint issues.
Sure.
So low on the priority list for actually.
Of course. Okay.
So this is I'm connected into the Perf Lab, which you've probably been in.
I actually haven't been.
You haven't been in there? It's a pretty. You should get a tour of that someday.
I would love to. Yeah, it'd be great.
I could arrange that for you.
Could you?
Yeah.
Well, why don't we do that?
So it's in the south end of the building. It's just on over in 26 South and 26 North. And in this lab, we've got some pretty monster machines, including something called a Superdome from HP,
nice.
Which is Itanium 2 systems that support up to 256 CPUs. And I'm remote desktoped into one of those. And here's Task Manager on this thing.
Nice.
can zoom in. I guess I don't have zoom in on this machine, but if you look at physical memory, it has 1 terabyte of memory.
Wow. Speaking of which,
you just mentioned that. It's got a terabyte of memory. Windows actually supports up to 2 terabytes of memory, and we have a system in the lab that has 2 terabytes of memory as well.
Okay.
But here you can see 256 CPUs there.
Now that's not a 256 core chip, so
this is actually a 128 socket chip. It's hyper-threaded. So there's 256. So there's basically 2 cores per socket.
So let me ask you a question. I mean, there's going to be sort of a cache line optimization issues as these start to grow, beyond that. Is that something that you think about at all? I mean, do you spend any time thinking about that problem?
No, I don't personally look at cache lines. So what these guys do is they've got multi-level caches, and the caches, they've got caches that are private to the CPU and caches that are shared across multiple CPUs as well.
Cool.
To try to get efficiency.
So can we see something manifest itself on here?
Well, I could run Notepad, and you could see.
Does Notepad equally distribute across all 256?
Yeah, Notepad does, I believe it does. Well, Notepad actually, if you run it, has a number of threads in it.
I'm sure.
Especially if you do a file open dialog, a bunch of threads spin up to do the file browsing population, the shell stuff.
All right.
They use the thread pool APIs, so to minimize the number of threads where appropriate. But anyway. I've got local kernel debugger set up here, and just to kind of tie together a few concepts that we talked about last time. Actually, let me see if I can put zoom in on this thing.
And this is related to NUMA and core aggregation or core chip.
It's NUMA and the group mappings.
Group mappings, yes.
Yeah, and you can see the mapping, the nodes, the NUMA nodes and group maps. So I'm going to just copy zoom it over to that system so I can show you a little more clearly what's going on. Taking a second to copy. There we go. Okay.
Cool.
Oh, you know what? I can't run it on this machine. This is an Itanium, I forgot. And I haven't compiled Zoomlet for Itanium yet.
Understood.
Actually, what I could do is minimize this.
So Itanium X6, Itanium 64, i64?
Itanium is i64. Yeah.
Which I
can do this.
thought I remember
There
it
we
was
go.
kind of a bummer for you guys to deal with. All right, let's see.
So this is the kernel debugger's bang NUMA command, which, like I said, shows you the number of NUMA nodes here, which is 16 NUMA nodes, the number of processors, 256. And then shows you a map of the NUMA nodes to the processors and the group assignments too. So one of the things we do when we assign groups, just to refresh what I talked about last time, is we try to minimize the number of groups we create. Okay. So on a 256-way system, we can have up to 64 CPUs in a group.
Okay.
Again, for backward compatibility with APIs that are designed for 64 processors, which was the max before. So to minimize the number of groups on this, dividing 256 by 64, we get 4 groups. So there's going to be these NUMA nodes, 16 of them, assigned across 4 groups. So that's 4 NUMA nodes per group.
Okay.
And if there's 16 NUMA nodes, that means there's 16 processors per node, and you can see that. Here's the map of showing that this node 0 here, which is in group 0, consists of these processors right there. And the NUMA node means that these guys have local memory.
So can we step back just real quick? So what this means is these guys are closer physically.
These guys are, connected to their own local memory.
Perfect.
So accessing that memory is more efficient than accessing memory on another node. And actually that's another thing Landy's done, is worked on NUMA APIs.
Okay.
And more NUMA support for memory management.
Nice.
Like one of the things he does is if memory is taken out of a processor's working set, it's migrated, or actually when it's faulted in from the standby list, which is memory that's been taken away from a process, but is still resident in RAM. So it's ready. It's kind of ready to be more quickly repurposed. If the process accesses it again, what it'll do is migrate the page's contents to the NUMA node that thread is accessing it from. So to try to get that memory closer to the process at that time.
Excellent.
So that's one of the changes he did as well.
Very cool.
So this is just showing you the map, like I said, of the NUMA nodes.
Cool. Well, I mean, it's the first time I've ever seen 256 task scheduler, task
Managers.
man, sorry,
Yeah.
task mgr.exe up and running. That's very cool. Kind of hard to read. You might have to scale that better.
Yeah.
Because we have 100, 1,000 nodes.
Giant monitor.
Yeah. So let's talk a little bit. So I think people kind of get NUMA. I think it might be kind of underappreciated by most people, but it's really important in high throttling output systems like servers, clusters. What else did we not talk about? I think one of the things that I was reading about internally is process reflection.
Oh yeah.
That has enabled some very interesting things like radar, which we've talked about on Channel 9.
Yep.
Can we talk about that a little bit?
Yeah, sure. So, you talk to the radar guys and they say they use process reflection.
Yeah.
One of the problems that we've got with trying to capture information about a process, or that we had before process reflection, is that you really want to capture the state of that process, basically capture what we call a dump of the memory contents of that process, so that we then can upload it to our error reporting services and then get it here so that we can take a look at what's going on inside of it. Or just actually get the dump locally and then analyze the process. And you can't analyze a live process because the process is changing its memory, and so you're not really looking at a consistent view of what's going on. The problem with capturing a dump of a large process is that it can take a long time to scan through memory, saving it to disk, or to scan through it as you're doing your analysis. And because things like radar they're kind of looking at potential problems, right? And they want to capture potential problems.
Sure.
Not things that we know about for sure, so you don't want to kill the process to capture a dump of it, and you don't want to stall it for too long because the user might actually be interacting with it. Or if you're on a server and you want to look at a process, it might actually be serving up clients, and you don't want it to stall because things will go haywire.
Sure.
You get a large server process and it could take tens of seconds actually to save multiple gigabytes of memory to disk. So that's where process reflection came into play. That came from the reliability team, wanting to capture more information about these kinds of things. So they took a look and basically came up with a modification of the fork code that was in Windows from the early days for POSIX compatibility, which is basically Unix standard API that was built into Windows. The thing with fork is was designed for an older era, and special processes that were voluntarily forking themselves. So, just realized what that sounded like.
Yeah. Go fork yourself, man. No, I like that. That's good.
No, it's
reflect
yourself.
Like yeah. All right.
So what reflection does, because we're coming in from the outside without the application's knowledge, want to get the process into a clean state as far as locks, the system locks, and second, when we clone the memory, don't want to clone parts of the address space that are mapped to devices, because even reading from device map memory could toggle the hardware. And so we come in our process that's mapped to device and toggle the device, it gets screwed up with respect to what it thinks is going on in the device. Okay. So reflection freezes the process temporarily, and then what we do at that point is capture a mini dump, which is just a basic amount of information, like what threads are in the process and their stack, and then do a full reflect the process. With the reflection basically makes the copy on write clone, the process continues running, and then we get a child process that we then capture a full dump on.
Oh.
And so I've got a couple tools that actually demonstrate that in action. So I wrote this tool. It's called KeyReflect, and it's just a demo tool. And actually, let me run something like Notepad so we can see this in action. So in Process Explorer, we can see that this Notepad process is right here, and it's a child of Notepad of command prompt. And you'll notice that if we look at its memory, it's got a working set of roughly 8 meg. It's got about 1.6 meg of private memory, and it's got 1 thread, which began its life in a Notepad startup. So if I reflect that process now, let me see what its process ID is, and then reflect it 5988. What we get is a child process of Notepad, which is the reflected process. So preflect now has a handle of this child, which is the clone.
Okay.
It's suspended so that it's not runnable. It's just basically a copy of its address, of Notepad's address space. And if you look at its thread, well, its main thread began its life in process reflection startup, not Notepad main, because Notepad's threads aren't in here anymore. It didn't copy the threads. And it's got a working set that's very small because the address space has been cloned, but preflect doesn't touch the clone's address space, so it doesn't actually demand any physical memory.
Perfect.
So that's just a demo of it in action, but I actually wrote a tool called procdump, which is on system terminals.
Nice.
Which has a -R switch. And what procdump's purpose is being able to point it at a process and say, if the process has CPU spikes of a certain duration, or if it has an unhandled exception, or if it terminates, then capture a dump of it. There's a switch that's enabled on Server 2008 R2 and Win7-R, which will enable process reflected dump. And in that case, it captures the same, what I talked about before, the mini dump followed by the clone, the reflection, and then the full dump.
So let me ask you a question about your old company, which still exists, but I mean, you know, in the mothership now, or the Death Star, depending upon how you look at it. The question I would ask is, some of those tools are incredibly useful, and in my opinion, more useful than some kind of what ships with Windows. Why don't we put those tools just in Windows?
Well, I guess it depends on your definition of useful. For my mom,
okay, fair enough.
They're not as useful. For the average, even pro user, they're not as useful because they're overwhelming. They really require you to have some clue about the system's behavior.
Okay, here's an example. Last night, I'm running, and of course, there's a service host background process running.
Yeah.
It's eating about, I don't know, 256 megabytes of my workable memory. And I'm kind of wondering, like, what the hell is it? Why is it doing that? It's kind of a lot. I'm not running a scan, am I? So, if it would be really nice to be able to click on it, and somebody wrote a tool many years ago, I used to use it from Toolbox, that actually would go load up all the DLLs that service host is, because that's what they do. They just load up DLLs and do things. Let you know what's loaded in memory, and you can actually look at the DLLs. Ah, it's this, and that DLL is part of, well, a Windows Defender, right, or whatever. So that's what I mean could be useful for the average user.
Well, so Resource
Manager does
Monitor,
it.
and Win7 has some of that functionality. So a lot of the Process Explorer type functionality has gone into Resource Monitor.
Cool. So that's a long round way to get to that. So you're still innovating.
But there's still there's still functionality that's in Process Explorer that's not in that tool, because actually I put in features in Process Explorer for a couple of reasons. One, first, to be useful. Second is to just give me an idea of what was going on in the system, how the system's put together. So I used it as a learning tool as well. And Dave Solomon in his classes, he'll say, hey, it'd be cool if Process Explorer would show us a process's I/O priority or memory priority, and so I'd go add that, which those things were introduced in Vista.
Okay.
So that's a lot of those things are there because of intellectual curiosity and just looking underneath the hood, not necessarily something that you can readily take advantage of in an average troubleshooting situation.
Sure. I mean, I understand. I mean, but it is nice to know you know, if my dad calls me and says something keeps eating up a lot of
Yeah.
my memory, it's like, well, that's because your antivirus program is running a scan. It does it all the time.
Yeah.
And a lot of times it's not going to say that in the Process Explorer. It'll be a service host.
Yeah.
So at any rate, we have more things to cover. One of the things that we haven't covered, and I know for a fact we didn't cover this,
Yeah.
and we really need to, is fair share scheduling.
Oh, dynamic fair share scheduling. That's another thing Arun also had a hand in.
Okay.
Yeah. So this dynamic fair share scheduling is a modification to the scheduler that was aimed at a particular scenario that's caused a lot of customers pain over the years when they've got a terminal server and they've got a bunch of users logged into the machine, and then one of the users fires up something that starts hogging the CPU, and that impacts everybody else on that terminal server. I mean, imagine you go to a web page that has a flash, one of those flash apps that gets in an infinite loop and just starts burning your CPU, which I run into occasionally, right?
Okay.
So let's say that you're on a terminal server, and let's just pretend it's a 1 CPU terminal server just for the sake of it. Somebody runs into that. Now their process wants more CPU than everybody else. It starts impacting all the other users that are trying to use the terminal server. Really what you'd want is, if you think about a terminal server, is to be able to by default have the server be fair about CPU usage across the users that are logged in, and ideally have knobs where you could say, well, prefer this user over that one because it's the CEO's account, or actually the admin's account, or whatever. I want to make sure that I get good time to the system's responsive to when I'm actually doing maintenance on the server. So that was a big request from the server guys, is this dynamic fair share scheduling, which in the scheduler now, if you've got the remote desktop role, it's been renamed from terminal server. If you've got that role enabled, then DFSS is automatically on. And when that is on, what's a session, which is the equivalent to a user being logged onto the machine interactively, all of the sessions are weighted equally by the scheduler. And so if you've got two users that want to consume, if you've got one user that's got something that wants to use 25% of the CPU, and another one that wants to use 100% of the CPU, or let's say 50 and 100. Okay. Without DFSS, depending on the way that the threads were using the CPU, the user wanting all that CPU time, that 100%, would actually end up getting more than 50% of the CPU, and the other guy would get less than 50%. I've actually got a demo of this in it that I show in my presentations.
Awesome.
With DFSS on now, the guy that wants 100 is shrunk down to 50, and the guy that gets 50 gets his 50 that he wanted.
Okay.
And so it's basically looking at how much, giving everybody a budget. It's saying there's two users on the machine, so each gets a budget of half a time period. And then it accumulates over one of these time periods the amount of CPU that the threads associated with that session are using. And once the guy hits his budget, then his threads start going into a queue that's the idle queue. It's the only run if nothing else is going on queue. Okay. Basically, they're put on the sideline. And that lets the other guys that want CPU to be able to use up their budget. If nobody wants the CPU, then it'll go back to this guys on the sideline queue and go, well, nobody else wants it, so here you can have the CPU again, which is above your budget.
Okay.
And then the next time, interval, the time interval ends, it resets, and starts doing the accounting again. And that's the basic idea to get things to be fair.
That's cool. One of the things that I want to talk about, without talking about, the next version of the operating system that doesn't exist.
Yeah.
So we're not talking about it.
Doesn't exist.
We're not talking about it.
Right.
So hopefully that's clear enough to the PR people. And fair enough. I get why they're doing that. It totally makes sense. So for you, what's like top of mind, right? When you step back and you think you have this general purpose operating system like Windows that is on, 92% of all PCs that are running at any one time. You support N number of configurations and hardware and driver. It's just crazy. But the fact that it works as well as it does, I think, is a testament to actually how good of an operating system it is in terms of general purposeness. What are the next big problems that technical fellows, distinguished engineers, PMs, vice presidents, what do you, when you look out, what are you thinking about? Because I know that's one of the things you do.
Yeah. Well, I can't really get into specifics. Right?
Don't get into specifics. It's not interesting. Well, they are, but don't.
Well, even talking about what we're looking at kind of implies
okay, fair enough.
kind of the directions we're going, right?
Well, concurrency.
Yeah. Well,
right.
Okay, so there's trends. There's some of those trends.
Trends. That's what I mean.
Yeah, like offloading to GPUs, heterogeneous processors, the explosion of cores. What do we do with those?
Yes.
So there's a lot of those kinds of things that we're looking at, and it's a tricky balance, right? Looking at and trying to predict what's going to happen.
Sure.
And where trends are going to go. And for example, the many-core thing, right? Where we're seeing this movement towards more and more cores, and yet we're not really seeing the killer many-core application. And
no, we're not.
We've talked to people in the many-core world, right? And people have been working on this for a long time. What is the killer many-core applications? We see little scenarios that can be enhanced with many-core, like and offloading to dedicated processors.
Sure.
Decoders, like the example that I mentioned, benefit from things like many-core, but we haven't run into this is an app that's aimed at consumer that really has a very significant experience jump when you go from 2 cores to 16 cores.
Yeah, exactly. Well, but that's sort of I guess, when I look at so there's a lot of operating system geeks out there. I'm one, you are kind of an extreme OS geek, and you always have been.
Yeah.
But the thing that I find interesting is, the operating system, the basic architecture of Windows is from the 1970s, man, right? The 1980s. Yeah. Big kernel. I mean, the NT was the one where you finally separated the shell and the kernel, but regardless of that, the kernel keeps getting bigger. And so I'm just wondering, like, in the future, like, do you guys think about, like, wow, how can we make either like modularize the kernel or split the kernel up more, blah, blah, blah. That's kind of what I mean by trends, not specifically what you're going to do, because that's long-term. This is long-term vision. This is not shipping products.
Definitely when we think about a day where there's 1,024 cores, for example, which is probably 10 years away, in any kind of kinds of scenarios, then we then you really say, should we be scaling up, scaling out? Should it really look like a distributed system? You talked to I'm sure the UMS guys and the concert guys, right?
Yeah.
Like, do we start assigning cores to specific workloads, doing high-level resource management that's above the operating system? Do we have instances of the OS that are assigned to particular groups of cores that dynamically grow and shrink? Do we have the operating system run just on a subset of the cores, where the operating system is providing some base services? Doesn't it necessarily run on all the cores? Some of the cores can be pure compute cores.
Yes.
So, yeah, there's a bunch of those kinds of things.
But it's fun. I mean, you're stoked.
Yeah.
I mean, in some sense, a 100-core machine, 128-core machine, 256 cores that you have up there, that's a distributed system. It just happens to be located on one piece of, like, one box.
Yes. Well, the hardware is distributed, right? Even the fact that you've got NUMA memory. And there's messages crossing buses and interconnects.
Totally. So, but when you get up to the cloud, then you get to deal with hundreds of thousands, and that's fun.
Yeah.
But anyway, to me, I think there are a lot of people that they watch these interviews and they love listening to this stuff, and we have to at least talk a little bit about some of the long-term things. I mean, you're a technical fellow; that's what you do. Now, I wanted to go back a little bit into history and ask you, kind of shifting away from Windows 7. When did you really start getting into operating systems? Because your history, which we know now from reading your blog and also from Channel 9 interviews, you were a troublemaker in some sense because you really dug into what the kernel was doing, and you always say, send bugs to us or whatever.
Yeah.
When did you really start getting into operating systems?
Well, if you consider Apple II's ROM an operating system, actually, no, it's before that. The TI-99 4A
Okay.
which is the first computer that I owned.
Wow.
That's when I started to get into the OS of it and really get interested in the systems part of it. And then I got an Apple II, which is really something that I really desired at the time. I'd played with Apple IIs, we had Apple IIs at school, but I didn't have one of my own until the school actually started selling some of the ones from the computer lab.
Okay.
And I got one through that. And then I became an Apple II ROM expert. There was actually a book that you could buy. You know, this is like the first, when PCs were still, were starting to get really enter the mainstream, right? So you could go to the bookstore and start to buy, there was a bunch of PC magazines, right, where you have ROM listings of machine code listings of programs like Moonlander and things like that that you go home and type in. But there was actually a book which was just disassembly of Apple IIsoft's ROM. And I go through and read that, and then I started to write extensions for Apple II's ROM. Like it didn't have a computed go sub, meaning in its basic, you could say go sub to line 10, but you couldn't say go sub to line I, where I was a variable. And a lot of the other basics had that capability. So by looking at the ROM, I figured out a way to add a routine, add support for go sub, computed go subs, and actually wrote one of those magazine articles for Compute magazine that you could go in and type in the code and get it. So it's really always been really where my heart's been.
Interesting, man. And yeah, I mean, it's great to have you here at Microsoft. Now, to give some props and some marketing for my PDC people,
Yeah.
because I've actually been more involved with PDC than I have been in a while. You're going to be talking in two capacities there. One is a very deep session on changes in Windows 7, and also you're going to be talking at the free day of Windows 7 training.
Yep. Yeah, it's very cool that you've organized. Actually, you had a hand in both of those.
Yeah. Well, but you know, thank you. I mean, the technical leaders track is something that I think will continue to evolve.
Yeah.
And be able to talk. You know, the idea there is what we just talked about. Like, what's on the mind of the people that are in the highest technical areas in Microsoft? What do you see down the line, right? And of course, you can't always talk about that because then people think that that's actually what you're going to do.
Yeah.
But yeah, I'm glad you're coming. Thank you for coming down. Yeah. What's your
speaking of, you know, I mentioned Landy and Arun. They're both going to be there with me.
Right on
that boot camp day.
Excellent. Landy in public.
Yeah.
Impressive.
Yeah.
How'd you convince him?
I walked next door. His office is next door, and I said, "Landy, let's do it."
Cool. Because we had him on Channel 9 once,
Yeah.
and I don't know that he was too into the camera thing.
Yeah.
But it sure would be good to see him down there, and we'll have that. But thank you for coming on Channel 9 and talking to us about these things, and we will continue to visit you.
Okay. Great.
Hopefully the next time we see you, who knows what we could be talking about.
All right.
Right on.
All right. Thanks.
Take care, man.